In this video, we're going to go over some basic logarithmic examples. So for logarithms, for any b greater than 0 and any b that's not equal to 1, this function here is valid, which states that y is equal to log b of x, where log b just refers to log and base of b. And this is then equivalent to x equals b raised to the y. So using this relationship, you can convert between the two and go from logs, which are usually kind of hard to work with, to exponents, which are, in my opinion at least, a lot easier to work with and what we're more accustomed to. So for this problem, the first one we'll look at, we can just simply rearrange it into the exponential form using the equation above. So we end up with 343 is equal to 7 raised to the y. And then we can go from here by just factoring our 343, which happens to break down into 3 7s. And so from this, we know that y is going to be equal to 3, which is then equivalent to, using the functions up above, log in base 7 of 343 is equal to 3. So that's just a quick example showing how to use this relationship to convert between logarithmic functions and exponential functions. Another important thing to note is that in cases where you are doing math, sometimes you end up using the natural log, which is written as ln, or sometimes called ln. And this is just equivalent to log base e to the times b, or whatever number you are going to end up using, where e is just the constant, which is equal to 2 point something that I don't remember off the top of my head. And so carrying with this example, just like with any other exponent or logarithmic function, ln of 1 is going to end up being equal to 1, since it actually can be arranged as e to the x, where x ends up being the 1 from this up here. Or actually, where x ends up being, or it can be arranged to this function here, where you end up solving for x with x being equal to 0 from the exponential 0 rule. Where b raised to the 0 is equal to 1. So that kind of gives you a pretty good example of ln and log and how they're related, which is this right here. And that's key to remember if you ever have to deal with the two, which most likely you will. So we're going to move on to our next decent example, which is log of 6, or log base 6 of 1 over 36. So with this, we can use the equation up above and convert directly into 1 over 36 is equal to 6 raised to the x, which if you go and factor, you end up getting 36 and 6 and 6, which we can then take and plug in by reducing the 36. We end up with 6 squared, since we have two 6's in the bottom, is equal to 6x. And then we can use the exponent negative rule to switch 6 negative second is equal to 6 to the x. And then once we have this, we can drop the bases since they're the same and just get x is equal to negative 2 in this case. So for a case in which you don't have a log of a factor of your base, so a log that's factorable by that number there, if you don't have one of those, or a log that's a multiple of that, then you can use a calculator to determine what you're working with by using the change of base formula. But if you're trying to do it by hand, it's a pretty involved process to actually try and solve a log by hand for a number that's not a factor of your base that you're working with. So a quick note before I say anything else, just for reference, when you're using your calculator, it's in common log, which is just log of x is equal to log base 10 of x, which is, and your calculator works in base 10, so that's the log you'll use when you're making calculations on a calculator. So for the actual example, we'll do one here where we have a log that's not exactly, it's factorable by 10, but it's not cleanly factorable. And so you'll end up having to, if you don't have a calculator to do this, it takes quite a while and you kind of have to make an approximation. So for this one, we can use that formula above, the one to convert from logarithms to exponents, to set up an equation where we end up with 5,000 being equal to 10 raised to the x, since we had y of log base b x is equal to, or is equivalent to, x equals base b times raised to the y. And so to solve this problem, we now have it set up in this form where we have 5,000 is equal to 10 to the x. And we basically can start by trying to factor, and 5,000 breaks down into 5 and 1,000, and 1,000 breaks down into 3 tens. So after seeing this, we know that this isn't going to cleanly factor since 5 isn't exactly a base of 10. And so we're going to have to go and use guess and check, basically, to try and figure this out. And we know that since we have 3 tens, that our answer should be somewhere between 3 and 4 when everything is said and done, because we know that 10 raised to the third and 10 raised to the fourth are on either sides of 5,000. So we have 10,000, and then we have just 1,000. So since this isn't going to factor easily and it's not going to make our lives a piece of cake, we basically just have to make a guess for x and then run with it and see what we can find. So my first guess is going to be in x of 3.5. And so then with 10 raised to the 3.5 power, we have to convert that into fractional if we're going to do this by hand, which is 10 to the 702, which comes out to be like 3,162.277. And since this is lower than 5,000, we know that we need to guess higher. So for the next guess, we'll go x is approximately 3.6. And so then we can take 10 to the 3.6 is equal to 10 to the 18 fifths, which is equal to 3,981.07, which is still lower than 5,000. And so we basically can just repeat this process indefinitely until we eventually zero in on what we're trying to get to. And for the actual hand calculations themselves, for this example here, what you would end up doing is taking 10 raised to the 18th times the 1/5, and basically break it up into the sort of problem where you then have the 5th root of 10 to the 18th. And then you just basically start at a close approximation and repeatedly multiply stuff together until you end up with 10 to the 18th being your answer. So for this one, we'd end up basically like taking like something in the ballpark of like 3,900 and then multiplying that by itself 5 times, and that'll eventually give us something in the ballpark of 10 to the 18th, and then we just have to repeat that. And that's how originally most of the logarithms were determined before we had computers to make everything so much easier, or calculators for that matter. So carrying on with this problem, we know that 10 raised to the 3.6 gets us to 3,900. So we still obviously got quite a decent ways to go. And I'm going to skip some steps because that's a lot of writing, and just say that we know x is going to be somewhere around like 3.698. And so if we take 10 raised to the 3.698, we'd have to find some sort of fraction for that, which would also be a bit of a pain. But if we do that, we'll end up getting, for our answer, 4,988.84, which is still lower than 5,000, but it's close enough that we know that we're pretty much getting to where we want to be. So then if we actually take the time to find the real answer, we'll end up with an x being equal to 3.6989700043,360, which is what we want. And that'll give us the answer to our initial equation. So we end up with a common log of 10 to 5,000 is equal to 3.69897. And if you have a calculator nearby and raise 10 to the 3.69897004336, you'll end up getting 5,000. And that's basically all there is to it. So thank you for watching, and hopefully this was helpful.